All right, so we're going to look at the chemistry history of atomic theory and a little bit behind that. So to kick things off, we have in 400 BC, Democritus and Leucippus used the term atomos. So atomos means cannot be divided. So it's this philosophical idea that if you take a bit of cheese and you cut the cheese, and then you cut it again, and you cut it again, and you cut... This is not a joke. This is actually what the philosophy was about. That eventually you would get to a piece of cheese that was so small, it could be atomos, not divided any further. And so this is the first theory. We get 2,000 years of alchemy after this, and from there we get to the 1500s. So the 1500s, we have George Bauer, and he wrote a book called Systematic Metallurgy. Paracelsus came up with medicinal applications of minerals, specific minerals and their medicinal applications. So this is where we start getting practical ideas, usable things out of alchemy. There's actually a lot of usable things from alchemy before this, but particularly at this point, we start getting more and more usable things. So 1600s, we get Robert Boyle's The Skeptical Chemist, Quantitative Experimentation and Identification of the Elements. 1700s, George Stahl, The Phlogiston Theory, one of my favorite theories of phlogiston, which you all know by a different name, oxygen. Joseph Priestley, The Discovery of Oxygen, and Antoine Lavoisier, one of my favorite chemists of all time. He's the one who actually figured out the role of oxygen in combustion and the law of conservation of mass, and the first chemistry textbook that was written. Just a beautiful story about Lavoisier and his wife and how involved she was, and how he got his head cut off by the French Revolution. That's not such a happy part. And then they apologized a year later to his wife, like, hey, sorry, we chopped your husband's head off. He was a smart guy. Anyway, 1800s, we get Joseph Proust, The Law of Definite Proportions, The Law of Composition, John Dalton, The Atomic Theory, and The Law of Multiple Proportions. Dalton's atomic theory, our modern atomic theory, actually comes from his, and it's not that dissimilar from his at all. Joseph Le Gay-Lussac, combining volumes of gases in the existence of diatomic molecules. Amadeo Avogadro, molar volumes of gases. Jöns Jacob Berzelius, The Relative Atomic Masses, the modern symbols for the elements. He's the one who gave us those. We get Dmitry Mendeleev, who created the first periodic table, and him and his research group actually showed periodicity throughout that table and actually predicted things that were missing. It's such a beautiful thing. J.J. Thomson, The Discovery of the Electron. Henry Becquerel, The Discovery of Radioactivity. In the 1900s, we get Millikan, who gave us the charge and mass of the electron, and then Ernest Rutherford and his entire research group, the existence of the nucleus, its relative size. Meitner and Fermi, sustained nuclear fission. Ernest Lawrence, the cyclotron and transuranium elements. Those are beyond uranium. So let's start with Dalton. So we have a lot of stuff that leads up to it. 1808, Dalton's atomic theory. He takes the idea of atomos cannot be divided, and he says that all matter is composed of extremely small particles called atoms. The atoms of any given element are identical in size, mass, and other properties. He's not completely accurate here on the mass part. The atoms of different elements differ in size, mass, and other properties. Absolutely true. Different elements, atoms, are different from the atoms of other elements. They behave differently. They act differently. That's what makes them different elements. Atoms cannot be subdivided, created, or destroyed. This is true, except in nuclear reactions. Atoms of different elements combine in simple whole number ratios to form chemical compounds, absolutely. And in chemical reactions, atoms are combined, separated, or rearranged. So modern theory versus Dalton. Dalton said atoms of a given element are identical in size, mass, and other properties. Atoms of different elements, different size, mass, and other properties. Modern theory says atoms of an element have a characteristic average mass which is unique to that element. And this is because of isotopes, which we'll get to later. Dalton also said that atoms cannot be subdivided, created, or destroyed. As I already said, Atoms cannot be subdivided, created, or destroyed in ordinary chemical reactions. However, these changes can occur in nuclear reactions. That's why nuclear is crazy. All right, so if all matter is composed of discrete molecules, then all pure substances have the same ratio of molecules and therefore the same mass on average. And water is always 2 hydrogen atoms and 1 oxygen atom. And the mass ratio is therefore always 2 to 16, because the mass of oxygen is 16, the mass of hydrogen is 1. So 2 times 1 is 2, and 1 times 16 is 16. So then we get J.J. Thomson. J.J. Thomson's name sounds to me like a great R&B singer, the man who you would want to be friends with, the coolest dude in the house. In 1987, J.J. Thomson used a cathode ray tube, which is a vacuum tube with electrodes on either end that fires electrons across a vacuum with high voltage. And he showed there's a negatively charged particle by adding a positively charged and a negatively charged plate on either side, and it deflected, which means that arc that's going through there is attracted to the positive plate, which means it must be negatively charged to be attracted to that, and he proved the electron. This is J.J. Thomson. He is not an R&B singer. He is an old, funny-looking white dude. His atomic model, he called the plum pudding model. He said, so that's a plum pudding. A plum pudding is a raisin cake, basically. He said there's a bunch of dough that's positively charged, and in that dough are a whole bunch of little negatively charged raisins in an atom that's really tiny. Now he's wrong. This is not what an atom looks like. Most of us know this is not what an atom looked like, but it was a great theory for the time. He knew there had to be a positive charge to counteract that negative charge. So in 1909, Robert Millikan determines the mass of the electron. So this experiment just completely blows my mind. It's the idea that you can take droplets of oil, spray them into a chamber, suspend them between a voltage, and using a microscope measure the diameters of the oil droplets and the charge to mass ratio or charge to volume ratios, and then plot all of those and predict where that intercepts the zero line, and you get the mass of the electron is 9.109 times 10 to the negative 31 kilograms. And he did all of this in 1909. It's just amazing. It's one thing to be able to replicate this experiment and create it after it's already made, but the idea to come up with it in the first place is just amazing to me. So the conclusion from the study of the electron with J.J. Thomson, the cathode ray tubes have identical properties regardless of the element used to produce them all. So electrons must be unique and present in all elements. Atoms are neutral, so you have to have a positive charge somewhere to balance that negative electron, and the electrons have so little mass that the atoms must contain other particles or something else to account for the mass. J.J. Thomson's theory was the dough, but we're going to find out that that's wrong. So Rutherford had an experiment. Rutherford took an alpha particle emitter. They didn't really know what alpha particles were or what it was, but they took and shot it at gold foil. That gold foil was then surrounded by a detecting screen, and they wanted to see what happened when those alpha particles, which are helium nuclei, we know that now, are fired through gold foil. The particles are fired at a thin sheet of this gold foil. They hit the detecting screen wherever they're deflected to. So if it's completely solid, you would expect them to be deflected backwards, but that's not what happened. They were deflected very slightly, and a few of them were deflected back. So if you shoot particles at something, in these pictures here, there's a target hidden behind the cloud. So figure out, if you have this coming in and bouncing off this way, and this coming in and bouncing off this way, figure out what this shape is and what this shape is. Let's call them figure 1 and figure 2. See if you can figure out what shape those are. So target 1 is a triangle. You can see by the way things are deflected that it's actually a right triangle, that those particles are bouncing off. Target 2 is what you'd see if there's a sphere. Slight deflection, major deflection, but a lot going right past it on either side. So what Rutherford found was that most of the particles passed right through, which told him that most of the gold foil was in fact empty space. A few of the particles were deflected. Very few were greatly deflected and bounced all the way back. He described it like a howitzer shells bouncing off of tissue paper. He actually expected all of it to go through, but it was almost like a giant shell, so a howitzer is on artillery, bouncing back, like a cannonball bouncing off of tissue paper. His conclusion was that there must be a nucleus, very, very small, and that this nucleus is very, very dense. It's where all the mass is. And that it's positively charged, and by being positively charged is why the positively charged alpha particles are deflected from it. So here's the conclusion of all of this research, is that we have electrons with a -1 charge, a proton with a +1 charge, and a neutron with a charge of 0. Our mass is 9.9109 times 10 to the -31 kilograms, and the proton and neutron have very similar masses, but they are in fact four orders of magnitude higher. The electrons are in the electron cloud. The nucleus is where the protons and the neutrons are. So this is a model of a helium-4 atom. It shows you helium. Helium-4 means helium with an atomic mass of 4, which means 2 protons, 2 neutrons in the nucleus. Tiny, tiny nucleus. And the electrons, 2 electrons in the outer cloud. Most of the mass of the atom is in the nucleus, and then the electrons are in the electron cloud. Most of the volume of the atom is empty space. So here's a summary of who did what and what happened and what the experiment was and all of that. Something good to take notes, a nice way to summarize all of those notes.